Okay, well let's go through another example. So let's say we have x1 through xn be random variables defined for the same space. And specifically, let's look at this space where we're going to say, let's flip a coin 10 times. If we end up with the heads, I'm going to pay you $1. So the number of heads we get times $1 is going to be your expected pay, or is going to be your payout. So what is your expected payout? Well, we could go through this exercise in two different ways. We could do it sort of the harder way, where we look at all possible outcomes. Well, I could end up having to pay you $0 if we come up with 10 tails in a row, or $1 if only one heads, all the way up to $10 if I end up with 10 heads. The probability of each one of those outcomes is a little bit tricky to figure out. So how many different ways can I come up with 0 heads? There's only one way, so tails on everything. But how many different ways can I come up with 1 heads? Well, I could be heads the first time, the second time, the third time, the 4th time, 5th time, 6th time, 7th time, 8th time, all the way up to the 10th time. So there's 10 different ways out of 2 to the 10 possible sequences. So it's not so bad for 0, 1, or 10, or 9. But how about 5? How many possible ways are there that I have to pay you $5? Well, I could have 5 in a row. I could have alternating, not paying you, not paying you, paying you. So those probabilities are not exactly easy to come up with. They will all sum to 1, and our expected value, our random variable for the expected, our random variable will still be any value from our set of possible values. But computing it this way is not going to be very fun. So you might be tempted to sort of do it that way. So our expected value here is $0 times the probability of $0 plus $1 times the probability of $1, all the way up to $10 times the probability of $10. But that becomes a very tricky probabilities to come up with, when we could do it a much simpler way. We could say that, well, x, our random variable x, is just equal to the probability or the amount of expected payout we should have for each individual flip of a coin. So we're going to say, instead of computing it the expected value of the sum, we're going to compute the sum of a bunch of simpler, easier expected values. So, for example, what's the expected value of a single coin flip? Well, I could pay you $0 half the time, or $1 half the time, which is going to leave us with an expected value of a single coin flip of 1/2. So, all I have to do now is sum up each of those coin flips, each paying out an expected value of 50 cents, and I'm going to do that 10 times. So my expected payout to you is going to be $5 if we flip a fair coin 10 times. Alright, well, let's start here with a trick question. So read this question and see if you can tell me what the expected value is for the total amount of rain over the weekend. Okay, so I called this a trick question because I give you more information than you actually need. So the key here is that it says the expected value for the amount of rain on Saturday and Sunday is 2 and 3 inches respectively, and that's the only information you need. Because you can always say that the expected value for the sum is equal to the sum of the expected values. And I've given you the expected values, which are 2 and 3. So your expected amount of rainfall is 5 inches. The rest of this is sort of misdirection to make sure you're sort of thinking about expected values and how you can combine them together. The key idea from one of our first slides here is that it doesn't matter if the two variables are dependent upon one another. So some of the key information is sort of hidden on this slide in that, okay, 50% and 75% were actually used sort of behind the scenes to compute 2 and 3, but that was done for you, so you didn't have to worry about it again at that point.